Okay, this unit is on energy. And energy is like the money of physics. It's going to make our life easier. Remember in biology, I would talk about ATP being the $20 bill. There are other molecules that have energy in them, but ATP is the most widely used and the easiest to exchange, just like a $20 bill. Well, for us in physics, energy is going to do this for us. Okay, so this is just an analogy. You don't have to write this down, but let's look at primitive economics. We used to have the barter system. You'd go do your job and they'd pay you by giving you 20 chickens to take home, right? It was fantastic. And I even threw in, I was hoping for some Diet Coke. I don't think that was part of their system. I think you got a goat and some chickens, but whatever. Now, modern economics, you do your job, then you get paid. And yes, I know money is the root of all evil, but I swear when they start to pay me in chickens, I am quitting. So you get paid money, and then you can go get your own Diet Coke. That's the way it works now. Well, for us in physics, this analogy is that we're going to use energy to simplify life, right? For the accounting purposes of motion and kinematics, energy are going to make our life easier. It's going to make our life easier keeping track of all this motion. All right? So motion in general, hard to calculate. We have forces, momentum, acceleration, blah, 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 blah. They all have vectors. Energy, it's just like counting the cost of something. It's not a vector, it's just a number, and we can see how valuable it is. Higher up it is, the more energy it has. Faster it's moving, more energy it has. And we can use those and say that those are always going to be equal in life because there's this thing called conservation of energy. And we can use that to simplify our math. Even some of those problems on that sheet that I gave you, the formula sheet, we didn't even use all of them, but they can get really, really complicated. And the nice thing about energy is that it is not that complicated. It simplifies things. All right, so here we go. Let's start simplifying. Now, I know you guys have already watched the Khan Academy because I told you to watch the Khan Academy on the potential energy and the work and to see how confusing those two terms are. Not the math, the terms. All right, so we're not going to worry too much about the terms. We're going to play here with the math. Potential energy is simply the energy an object has by being up high. If I had, a nice little rock that I wanted to drop on a student's head because they were sleeping, if I dropped it from 1 inch up or 2 inches up, there wouldn't be a lot of energy. It wouldn't be a very big impact. But if I dropped it from the top of my ceiling, say, there would be a much larger impact. There would be much more energy in that rock, and that is simply the location of the rock. So we are assuming here that we are in Earth's gravitational field. Otherwise it doesn't work. You need to be in a gravitational field. And all you need for this calculation then is the mass and the height. How big is this rock and how high up am I holding it over a student's head? Gravity will do the rest for me, all right? So just the mass and the height. See how simple we're going? And we can think of this as an energy bank. The higher up something is, when I release it, I'm going to increase its velocity. I'm going to get some energy out, a mechanical energy in the form of kinetic energy. But right now, it's like a spring being loaded. It's just sitting there waiting to be dropped. The unit we use, and I know you already know this from Khan Academy, but the unit we're going to use is the joule. Okay, so let's look at this little sample problem we have here. We have a 6 kilogram ball and it is floating in midair, or we should assume it's falling since it's on Earth. To find the potential energy at the height of 20 meters, again, simple calculation. We know the mass, 6 kilograms. We know the height, 20 meters. Multiply 6 kilograms times 20 meters. And then we just need gravity, and we can round for these purposes. 10 meters per second squared is fine. So you get 6 times 20 times 10, and you get 1,200 joules. 1,200 joules. And then when it's on the ground there, when it's dropped and it's on the ground, it's no longer such a danger to whoever's student. I'm holding this over their head. It's fine. It's on the ground. It will have no potential energy at zero height because the height is zero. So if you multiply something by zero, the other side's going to be zero. Your potential energy will in fact be zero. Not to say it can't have other kinds of energy. We're going to assume that there's some velocity right before it hits. And on impact, you'll actually get some heat generated. So I'm not saying energy goes away magically here. There's conservation of energy. It is conserved. It's just not in the form of this potential energy waiting to be dropped. All right, work. Work is related to energy, and in fact, it's going to be in the same units as energy. It's going to be in joules as well, but we're going to use it a little differently here. We're going to say work, in this case, is defined by the force applied to an object and the distance it traveled. And at first you think, well, I have a block over here and I apply a force and now it's over there. How would that have more energy or anything like that? I haven't really done anything. But remember, when you do these equations, it's going to be at the instant you stop. And if we apply a force, take apart force, that's mass times acceleration. This block is now accelerating. So we have actually added energy to this block. Take force apart here and add ma instead, mass times acceleration, and then distance. And you're going to see that, in fact, we are adding energy. If we do work, we take force and we apply it over a certain distance, that block will be accelerating. In the real world, there's friction that's going to be acting against you. And so we don't think of the fact that, in the world of physics, we always take friction out and air resistance because that's oh so accurate. But it's the way we do the math. So we're not going to, if we don't calculate the negative force, the negative work done by friction, you will have added energy to that block. It will be accelerating. Okay, so force acting in the direction of motion is positive work, right? If we're going to the right and we apply force there, it's positive. Force acting opposite direction, negative work. What's always the most negative thing in the room? It's friction or air resistance. I'd hate to meet them if they were a person. All right, force perpendicular to the motion. This is most often your normal force. This is what's supporting it. Zero work. It's just not playing the game because it's going in the wrong direction. Here is an example of work. So we have these guys on the right and they're lifting a sandbag. And in one case, so look at the examples. It's going to say twice as much work is done lifting 2 loads, 1 story versus 1 load for the same distance, right? So if I lift twice as much mass, then I get twice as much work. Another way of doing it, though, is to say you can do twice as much work is if you lift 1 bag 2 stories, right? If you do 1 bag and you go twice as high, twice the distance, you're going to do twice as much work. This all, they take this as proportional to lifting 1 bag 1 story. So that's why it's twice as much if you go 2 stories, or it's twice as much if you lift 2 bags. Okay. Work. Your unit of work is a joule Newton meter. Remember, force times distance, but we shorten a Newton meter to a joule. All right, so let's check ourselves. You have slaves pulling a heavy load. Look, they look like TAs working in my classroom. The work done by slaves, is it positive, negative, or 0? Well, they're pulling in the direction we want to go. That's a positive pull. That's the direction we're going. What's the work done by friction? Well, friction's always negative. And then the work done by the ground, the supporting one, remember I said if it's not going in the right direction, it's not playing this game, it's actually doing no work here. It's neutral. It's not doing anything that increases the work. Okay, so we have potential energy, which is a form of mechanical energy. And now we have kinetic energy, which is another form of mechanical energy. And these two ones are very, very often conserved. Not always, but almost always. And for the purposes of our calculations, these are going to be beautiful things. The kinetic energy of an object is, the kinetic energy is 1/2 mv squared. So write it, Ke equals 1/2 mv squared. It's a beautiful thing. It's a simple formula. It's actually derived from one of the formulas we gave you a long time ago for velocity on your formula sheet. But in this form, it's going to be very, very easy to use because we can just compare it to the potential energy. How high was that object when we dropped it? And then we can find the velocity at the lower spot, and the masses should not change, right? You have, on the one hand, for potential energy, you have the mass, and then on the kinetic energy in that formula, you have the mass. Almost 100% of the time, you can get rid of mass in these. They just go bye-bye. You don't even need to know the mass because it's on both sides of the equation. It's a great thing, but we'll get there later. All right, so kinetic energy is the energy of motion. Something that's stationary has no kinetic energy. And it's related to momentum, but it's not actually the same as momentum. Yes, it has some of the same things in there. There's mass and velocity in there. But energy is different than momentum, and there's a square in there. It's the velocity squared, and we're going to see the importance of that pretty soon here. Okay, so here's your sample problem again. Recognize that one. What is the kinetic energy of a 6 kilogram ball falling from the height of 20 meters just as it reaches the ground? Well, we already did the math. We did that math. You can take the potential energy, which is mhg, mass times height times gravity, and you just multiply it out, you get 1,200 joules. So guess what? It's 1,200 joules at the top, it's 1,200 joules in the middle, it's 1,200 joules at the bottom. Not all in kinetic though, that's a total energy. So at the top, it's 100% potential energy. And at the bottom, right before it hits, it's 100% kinetic energy. So we take that 1,200 joules and we can actually figure out the velocity using the formula 1/2 mv squared. And yes, we will be doing these for daily questions and just for fun. All right, here's the big idea. You have a 20-meter block, you have a 20-meter, ball up high, and then it falls 20 meters. So you've lost the potential energy, you've gained the kinetic energy. So up high, 1,200 joules of potential, no kinetic. Down low, no potential energy, it's all kinetic energy. Somewhere in the middle. We can actually do these calculations. We know that it's something in the middle. In this case, they gave you perfectly in the middle. But if they don't give you something perfectly in the middle, you can just find the height and redo potential energy, mgh, and you will find it again. So that's, again, a nice, easy calculation. Okay? We can do it on a ramp. We can do this thing doing circles for all we care. It doesn't matter. That's the beautiful thing about energy. It doesn't matter how the ball gets there, as long as it gets there. All right, it can take that path. We don't care. You can have it loop-de-loop, and yes, this is where roller coasters come into fun because they can loop-de-loop before it gets there. It makes no difference. As long as it gets there, we can find the kinetic energy. When we find the kinetic energy, we can find the velocity. Okay? And that's why it's the currency of motion. It doesn't depend on the path. We don't need a straight line. We don't need anything like that. It's straight up this height times the mass times gravity, and you have potential energy. And from there, you can use it to calculate your velocity and your kinetic energy. All right. So, thank goodness, energy is conserved, and mechanical energy is conserved. So, potential energy plus kinetic energy is the total. So we can look at the potential energy plus kinetic energy, first, and it better equal the final thing. So the potential energy plus the kinetic, when we drop the ball, that total better equal the ball at rest. Okay, let's look at a pendulum. Because as you pull a pendulum back all the way as far to one side as you want to go, and you're sitting there. It has all the potential energy in the world because it can drop a certain distance. You haven't released it, so there's no kinetic energy at this point. It's all potential energy, right? We release it. It's somewhere in the middle of its swing. It has potential and kinetic energy. It has both of them. Yes, if we calculate the height, we could find how much of what. Okay, then at the very, very bottom, right before it starts to swing up, it's not swinging up yet. That little blue arrow is a little deceiving. It's at the very, very bottom of its tether. It has no more potential energy. It's not going to fall any farther down. This has converted it to 100% kinetic energy. This will be as fast as you can go. All right, as fast as you can go there, and it's going to swing up, and it's going to convert to having some kinetic energy, and then finally it's going to go up to the maximum height, which is again all potential energy. And then of course that whole process reverses itself. Okay, so we can predict the speed from that, but we also know that there's no magic in a pendulum. It will not go higher than its original starting point. No matter what you do to it, it can't go higher unless you push it. That's adding extra energy. That doesn't count. I don't even know why you guys think of that stuff. No, if you just drop it, it can't go any higher, right? It could take a weird path or whatever, but it's got to stay at that height or lower because of air resistance. Okay, so let's check ourselves as to why kinetic energy matters. Let's say you're going 30 miles an hour in a car, and another car is going 60 miles an hour. How much more times does the kinetic energy have? Well, go to your kinetic energy formula, pull it out and take a look at it, and you're going to see that it says kinetic energy equals 1/2 mv squared. Squared. Not 2 times mv, no, squared. We're squaring that. All right, so it's going to end up with 4, not double, squared. It's going to be 4 times the amount of kinetic energy. If you have 4 times the amount of kinetic energy, and then we need to stop it, that's your force times your distance, right? You're going to get 4 times the distance to stop your car. This is why speeding is bad. Bad. Yes, I tell this to my son all the time. All right, here is, a stopping chart for some different speeds, but it basically will tell you that ignore the reaction time. All right, you got a reaction time. Yes, the faster you're speeding, that reaction time, you have traveled a longer distance. But then look at just the physical distance to stop the car, right? You have this physical distance to stop the car. Once you have applied the brakes, you are going to be doing 4 times, for double the speed, 4 times the braking distance. That's why people who tailgate just piss me off all day long. Gonna flick a booger on their windshield. Okay, so let's look at work and energy. So you can get to the same place a couple different ways in life. You could be the big, brawny guy on the right who's just gonna lift the block straight up and apply a large force for a short distance, or you could be the smart female on the left who's gonna do the exact same thing but slide it up the ramp. Takes less force, but you have to do it a little longer. This also goes to the, as we look at efficiency and we look at simple machines, there is no such thing as a free lunch. So no such thing as a perpetual motion machine, I want to point out. There's also no such thing as a free lunch. If you're going to get there, notice she has to do the longer distance. Sure, the force was less. This is just a simple inclined plane. We can call that a simple machine if you like, but the distance is longer. So you get the overall same amount of work, but the distance is longer. Smaller force, so you don't have to really exert yourself, but you got to do it longer. All right. So as we look at machines, you're going to get work in equals work out. There is a conservation of energy. And when we look at that, that's the force, the input force times the distance is going to equal the output force times the output distance. And yes, you can make that input distance really big so that you can apply a very small force and just do it for a longer period of time, and then you can have little kids move things, or you can move very large things and make your life easier that way. But you will be increasing the distance. There's no free lunch here. You got to increase the distance. You got to do something to make these work. All right, so simple lever. Yeah, I know, I'm kind of on a roll here, but if you're gonna, see if I can get my little red dot to work. Yeah, here it is. All right, so here you go. This is the distance you're lifting this block, all right? And we can have a large force over here, and you can apply a small force over here, but you're applying it for a longer distance. 2 or 3 times the amount, depending on the location of your fulcrum here. Maybe 3 times the amount. Yeah, I'm not really sure. There's the middle. But the idea here is that you're going to do a longer distance here. You're going to do less distance here, but you're going to get a greater force. That's all cool, but there's no free lunch. All right, block and tackle. Here we go. Still multiplying the force. Watch this. At first, you look at this and you're like, no, it's not. No, that's not multiplying the force. No, it's not. Yes, it is. Watch. All right. Little Susie so-and-so, she's pulling up here, right? Let's say she pulls up here 1 meter. She pulls up this piece of rope here, up by 1 meter. How far does this go up? Well, let's follow the rope. She's pulling up here by 1 meter. This is suspended in the middle. Goes down and around. Did she pull this part by 1 meter too? No. She pulled 1 meter up. It's got a split between these two sides, which means the center part only rises by 1/2 meter. Okay? So yes, again, no free lunch. She can pull this up with half the force, but she's going to do twice the distance to do that. Why? Because this ropes around. This is a free floating pulley. It's actually different if you attach it up here. But in this case, I want you to take a look at it and notice that to get this to go, she has to pull 1 meter, and that's going to give her a 1/2 meter rise. And that's because the pulley is looped underneath. So she'll pull 1 meter up here. The thing would just be cattywampus. It's gonna recenter itself, and it will rise 1/2 meter. All right, let's look at efficiency. Efficiency. That's the percentage of work put into a machine that's converted to useful work, the output. So useful energy in, total energy in. Oh, useful energy out. Excuse me, I said that wrong. Useful energy out. What can we get out of it compared to what we put in it? Machines are not nearly as efficient as we would like to think they are. I'm just saying, they're not. Even photosynthesis isn't that efficient. Power, all right. Power is pretty simple. It's just how much work is done in a certain amount of time. How fast can you do the work? Faster, better. Faster is more power. So it's not just the work done, it's how fast you can do it. All right, and it's named after Watts, James Watts. And yes, you know I love James Watts. Totally helped develop the steam engine. Did this whole separate condenser thing. Made it way, 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 way more efficient. It was like a Newcomen machine or something before. It wasn't doing hardly anything. Good old James came along. That's Mr. Watt to you. And totally fixed the system. And I'll stop going off on that because I know it's not history. But you're going to have watts. That's going to be your unit of power is a watt or a kilowatt. Yes, you're used to seeing this with electricity, but there's other places that have power. It's a joule per a second. How many joules per how many seconds is our unit of power? And it's going to give you a watt.